a very exciting, historic moment. I'm Peter Stone, professor of computer science at University of Texas at Austin. I have the great honor to introduce the very first invited speaker of the joint sessions of AMOS, IJCAI, and ICML for the first time ever. For those of you coming in, there's lots of seats over here, by the way. So, Joyce Chai is a professor in the Department of Computer Science and Engineering at Michigan State University, where she was awarded the William Beale Outstanding Faculty Award in 2018. She holds a PhD in computer science from Duke University. Prior to joining MSU in 2003, she was a research staff member at IBM T.J. Watson Research Center. Her research interests include natural language processing, situated dialogue agents, human-robot communication, artificial intelligence, and intelligent user interfaces. Her recent work, which we're going to hear about today, is focused on situated language processing to facilitate natural communication with robots and other artificial agents. So without further ado, Joyce.
Good afternoon. It's a great honor for me to be here today, and I would like to thank conference organizers for inviting me. And first, I'd like to say that I'm very lucky to have an opportunity to work with a group of talented graduate students. Without their hard work, this talk would not have been possible. Okay, so I will start with a question to the audience. What TV show is this? The Jetsons. Yes, if you have not watched it before, The Jetsons is an American television cartoon series. The first episode was aired in 1962, which was about over 50 years ago. So Jetsons is a family who lived in the future. Besides Mom, Jane, George, Dad, George, and the two kids, they have this robot maid called Rosie. So Rosie does all the house chores for the family. So I'm just going to show you a couple quick clips.
Well, we do have one old demonstrator model with a lot of mileage. Rosie!
Coming, sir. Here I am, sir. Yes, sir.
The old girl's still eager, isn't she? But of course very H-O-M-E-L-Y.
I may be homely, Buster, but I'm S-M-A-R-T smart.
I like her, and I'll take her.
Is it too loud?
Oh, thank you, ma'am. Thank you.
Is this too loud? The volume is good?
What's this about inviting Mr. Spacely when all we have in the place is leftovers?
I didn't invite him. He invited himself.
All right, break. When did your boss get here?
And he split second.
Where are the leftovers?
In the kitchen.
Never fear while Rosie's here.
How am I going to explain needing a raise when I've got a luxury like that monster clanking around?
We'll just have to keep Rosie out of sight.
Come and get it.
So it's really fun to watch this show. Actually, you may find some resonance with today's world. So for example, just in the first episode, you're going to see this little thing moving around when the button is pressed. So does that look familiar to you? Robot cleaner. And you're also going to see this kind of thing a lot. I'm just wondering, for all of us who are here, who has not done that before? So now comes the big question. What about Rosie, the robot maid? Today, we have AI systems that do vision, language, robotics, but how far away to realize this Rosie, the robot maid, who can do the housework for us, who can communicate with us in language, and who can even defend herself against discrimination? The truth is, despite tremendous advances in AI technologies, we are still far from having Rosie the robot maid. However, the progress has been made. 15 years ago, when I started my NLP group, I would not have dreamed of having physical robot in my lab. And today, my students and I had opportunities to work with a few different kinds of robots. So the availability of robotic infrastructure, recent advances in computer vision and machine learning have really paved the way for us to study language communication with robots. So today, I will talk about a particular kind of a language communication, which is to teach robots new tasks and task-related knowledge. So imagine in the future, you can rent or purchase a robot, just like Rosie. And the robot comes with some pre-existing knowledge and skills, but the robot doesn't have anything knowledge about your household. There may not be large amount of data available, and you may not want to wait for the robots to explore the environment by itself. Certainly, you don't want to risk the potential damage caused to your kitchen, and you're not a technical expert who can program the robot. So what becomes really ideal is for you to be able to teach the robot as if you're teaching a human assistant. So this has led to an emerging field on interactive task learning. So part of which is to address how to teach artificial agents new tasks through natural interaction and communication. And there has been an increasing amount of work in various communities to address this problem. And in general, there are two kinds of interaction that can facilitate transfer of a task knowledge. The first kind is the demonstration of the tasks. The humans can perform the tasks and the robots can learn by observation. Or the humans can provide guidance for the robots to follow and learn from there. And the second kind is the direct specification of task structures, constraints, and properties. And in many cases, interactive task learning involves a combination of these two. And as you can see that, natural language communication plays an important role. Next, I'm going to show you a quick demo where our research assistant teaches our robot how to make a strawberry smoothie.
Hello. Hello. I'm going to teach you how to make a smoothie. First, you get the knife and the cutting board.
I don't see a cutting board.
This is the cutting board in my hands in front of me.
Okay.
Next, you take a strawberry and you cut the leaves off.
What do you mean?
You cut the green part here off the strawberry.
How do you do that?
Using a knife like this.
Okay, so you get the idea. In fact, this is not a functional system. This is just a demo we made a few years back, trying to demonstrate the idea of carrying conversation to teach robots new tasks. So at the end of a communication, the idea is for the robot to acquire this grounded task structure. As you can see here, the structure captures the hierarchical relationship between the task and the subtasks, and it keeps track of the partial order between action steps. And participants of the actions are grounded to the perceived environment, and actions also comes with action specifications and the resulting states that are caused by these actions. So you see that the structure is rich in representation, so it has several advantages. First, it will provide a common representation to bring humans and robots come to a joint understanding of the situation. And it will also allow the robot to reason about the tasks and plan for actions in the future. And you see that these semantic labels are grounded to the perceived environment, so it provides opportunities for robots to communicate with humans in language. However, arriving at this task structure is very complex and faces many challenges. One of the key challenges has to do with the very nature of human language communication. So in human language communication, what enables us to understand each other is this notion of common ground. So the common ground includes mutual knowledge and shared beliefs. Being perceptual co-presence also supports common ground. For example, we're all here co-present in this joint environment, so we have the same perceptual access to this environment. If there is a loud noise happens in the hallway, and I believe you're going to hear the same noise as I do, then I can use the expression that noise to refer to it, and you would not have any problem understanding me. And common ground also includes shared past experience. If you and I went to a restaurant together last night, and you and I both know that we were there at the same time, then I can use that restaurant, and you would not have any problem understanding me. So common ground is key to communication success. When common ground is missing, then the communication between partners becomes extremely difficult. So then let's take a look at what happens in human-robot communication. So humans and robots are co-present in this shared environment. However, they have a mismatched abilities in perception and reasoning. So their representation of the shared environment are significantly misaligned. So even being co-present, they don't have a shared perceptual basis to start with. And then on top of that, humans have a tremendous knowledge about how the world works, and humans can create or generate these instructions to describe actions in their minds spontaneously. But on the other end, the robot has very limited knowledge, so it'd be very difficult for the robot to map that to its own internal representation. So they don't really have a common ground to support their communication. And what makes situation even complex is this presupposition. In human communication, we assume that we share the same kind of a world knowledge. So we don't have to explicitly state every piece of information. So if I tell you these 3 steps, you would not have any problem understanding me, and you'll be able to perform the action. This is because you and I both know that the strawberry has to be put somewhere first in order to be cut, and some tools will have to be involved to cut the strawberry, and the blender has to be open in order to put the strawberries in. However, if you tell the robots these 3 actions, 3 steps, robot doesn't have this same kind of a background knowledge. So it'd be very difficult for the robot to understand what these actions mean and to learn the task structure. So this brings up some important question. What kind of a common sense knowledge is essential for understanding and modeling action verbs in order to help build common ground and bridge the gap of presupposition, and then how to acquire such knowledge? So with these 2 questions in mind, for the rest of this talk, I will share with you some stories about these concrete action verbs. And particularly, I will talk about 3 problems: grounding language to perception, to action, and action effect prediction that is important for task learning. So in grounding language to perception, I'd like to say a few words about verb semantics. So in linguistics and computational linguistics, verb semantics are often captured by frames. So these frames specify key ingredients that allow the understanding of the situation involving that particular action. So these key ingredients are often called semantic roles or verb arguments. So for example, the frame for the verb take specifies the taker, things taken from, and things taken to. And in natural language processing, one of the tasks is to automatically identify these semantic roles from text. If we want to support language communication with robots, we have to take one step further. So we have to ground these arguments to the physical environment. And if you notice here, the agent and the destination are not explicitly specified. This is an instance of a presupposition, but in this case, they can be implied from the vision. And we call these implicit arguments. And the robot will have to ground both explicit arguments and implicit arguments in order to reach a full understanding of the action. So to help out, to start our investigation, we use this TACOS data set, and I think some of you probably are familiar with this data set. So this data set consists of parallel video and language descriptions describing activities in a kitchen domain. So we took a closer look at a set of commonly occurred action verbs in this data set. And here, this table shows that the red bar shows the explicit roles and the blue bar shows the implicit roles. And as we see that patient role, the objects are always explicitly specified. This is not surprising because these verbs are all transitive verbs. And some important roles are not explicitly specified, but they are very important. For example, tools. Tools are very important to understand and perform actions. So the good news is that the verb frame semantics allow us to construct a graphic model that support grounding these both the explicit and the implicit roles to the perceived entities in the environment. So we extend a previous approach by Telex to address this problem. And here we have some initial results. The light blue bars is just the grounding performance from the annotated division. So we manually annotate a part of the data in terms of the bounding boxes, object track, object labels. And the dark bars here, the results from automated vision. And this is a collaboration with Song Chunzhu's computer vision group at UCLA, and Cai Mingxiong applied the state-of-the-art computer vision techniques to process this data. And as we can see that vision processing still faces many challenges, especially in unconstrained environment. So then the question is there any kind of a knowledge, okay, from the language we can use to help the agent to actively perceive the environment and to better ground the language to perception? So let's take a closer look at what happens to the world when these action verbs are used. So he takes out a cutting board. The location of the cutting board changes. She rinses the cutting board. The residuals on the cutting board disappear. She peels the cucumber, peels the cucumber, the color appearance of the cucumber changes. She cuts the cucumber become multiple pieces from one big piece. So we humans actually have this kind of knowledge about how the world changes given a particular verb. And in fact, if we don't even see the scene, we can anticipate, okay, what change will happen to the objects of the verbs. Linguistic studies have also shown that concrete action verbs often denote some change of state as a result of action. But however, there wasn't any prior work that took a closer look at detailed dimensions of state change that can be associated with the concrete action verbs. So we took an investigation, took a look on this problem, and our question is whether we can model these causality explicitly, and whether such causality modeling can allow the basically provide some higher level guidance for the robot to actively perceive the environment and ground language to visual world. But the one problem is we really don't have any data to start with, because this kind of a knowledge is so fundamental and pre-assumed among humans. We don't see that in any of the communication. So instead, we use the crowdsourcing study. We give the crowd a set of verb-noun pairs and the corresponding videos, and we ask the crowd to describe in language what kind of a change might happen to the objects of the verb. So from there, we collect a data set of action, effect, description. As we examine these verbs, we notice that these result verbs actually specify some movement along certain scale. So this has a similar behavior as the gradable adjectives or scalar adjectives, because their semantics is defined in terms of a scale system. So then, motivated by this typology for adjectives, we identified 18 dimensions of a change, which can be potentially perceived from the environment. So since they can be perceived, the idea is we probably can design some kind of perceptual detectors that would actively look for those changes. So given a verb and its causality knowledge, it can trigger the perceptual detectors. And here we're mainly looking at visual detectors that will allow the agents to perceive the environment. And we incorporate this into two approaches. One is just the knowledge-based, ground the arguments to the objects that are compatible with these visual detectors. And the other is model these detectors as the intermediate features in the graphic model. And this chart shows some of the results. So the blue bars here are the results from the graphic models which don't use any causality modeling. And the red and the green bars are the result from the causality modeling. As we can see that, okay, the causality modeling actually helps here, improves the performance. But then you may ask, okay, great, if a verb has a known causality labels, okay, then you can trigger these detectors. What if the robot encounter a new verb-noun pair, okay, which the robot doesn't have any knowledge about? Can the existing knowledge base help to predict the new causality labels for the new verb-noun pair? So to address this question, we did additional experiment. So our assumption is that if the new verb-noun pair appears in the same context as the verb-noun pairs in the knowledge base, then it's very likely they share the similar kind of causality labels. So based on this assumption, we just use the GloVect to capture the verbs and nouns and just train a very simple MLP for multi-label classification. And these results based on the close to 800 verb-noun pairs we studied. And the results show that for a new verb-noun pair, if the verbs and the nouns are already in the knowledge base, there is a decent chance to get the causality labels correct. And also in this particular domain, nouns seem to play more important role. If you know the noun but you don't know the verb, you still have a pretty reasonable chance to get these causality labels predicted. So that's the part on the grounding language to perception. Now comes another question. Suppose the robot can perfectly ground all these verb arguments to the environment. Can the robot perform the action? The question is no, okay? So before I start working with robots, I thought robots are smart. But then after I start working with them and I realize they're not very smart at all, okay? At least some of the robots. For example, for a typical robotic arm, it only knows 3 basic actions: open gripper, close gripper, and move to. And the space of these actions is often defined by some formal language. And if you want the robot to put the apple on the plate, that action will have to be first translated to these primitive sequence of primitive actions. And the heart of that problem is planning. So next I will talk briefly about the second problem, grounding language to action, taking use of the planning. So let's say that we can teach the robot the new verb or new action stack through these step-by-step instructions. Open gripper, move to the one block, and the close gripper, move to another block, and open gripper again. And at the end of teaching, the robot tries to capture the knowledge to represent this action or this verb. So is it the case that first representation that just simply capture the sequence of primitive actions, or you capture the resulting state that robot's being through by using these primitive actions? So which one is better? So as it turns out that the second one, the state representation, is a better representation. So if this is actually nothing new, if you know how planning works. So because it is more generalizable, it can be connected with the symbolic planner to come up with sequence of action. So you can teach the robot in one configuration, and the acquired knowledge can be applied in a different new environment. And we call these a state representation the grounded verb semantics. So then the question is how to acquire these grounded verb semantics. So let's first take a look at how children acquire language. So there are different theories about child language acquisition. And the theory I am particularly drawn to is this social pragmatic theory, which was developed by cognitive psychologists, most prominently Michael Tomasello. So what this theory says that is the children acquire language is kind of a byproduct of a social interaction, much the same way as how they acquire other social conventions. So at around 1 year old, the children develop this very basic cognitive skills, such as intention reading and pattern finding. So these skills allow children to acquire linguistic constructs from the interaction with their caregivers. So the constructs start with something simple like words, and then becomes a mixture of words and generalization, and then becomes more complex abstract construction. And the construction acquired earlier will be used to acquire more constructions as interaction continues. So motivated by this theory, we developed an incremental approach to acquire grounded verb semantics. So this approach consists of two phases. Either the robot or the human can initiate this learning phase, where the human teaches robot a new action. And through its own experience or by observation, the robot will generate or acquire a new verb representation or update an existing representation. So that's the learning phase. And the execution phase, a command from the human will trigger the execution phase. So once the command is received, the robot will look at its knowledge base, find the most fit verb representation, and use that to do the planning. And based on the outcome of the planning and the execution, the human can provide feedback. So if it's not correct, it can initiate another round of learning. So through this learning and execution, robots can continuously acquire new verb semantics through interaction with humans and environment. So I'm going to show you, this is an example of how to teach this virtual Baxter fill the cup with water through the step-by-step instructions. And you see the pick up the red cup and move to the left and so on. So through these instructions, the robot will experience the change of a world from the initial state to the resulting state. So here you see that we actually made several simplifying assumptions, right? First, the world can be captured by a closed set of predicates. And here the world is the deterministic, but certainly that's not going to be true, right? So I will talk about that in a couple minutes. But this will get us started. Okay, so the red part indicates the differences or change of state. If we capture that, we can form a single hypothesis to represent the verb semantics. But this is very specific, okay, to this particular learning experience. To make it more generalizable, we can just use the difference to base hypothesis to capture the difference and build a very classical kind of specific to general hierarchy to capture the concept of the resulting states. And the part of the state, part of the space that's not consistent with the learning experience will be pruned. So you can imagine that through this continuous interaction, the robot will acquire like these hypothesis spaces for a variety of verbs. And when new command come in, the robot will try to find the best fit hypothesis. So then there could be different ways to learn how to select the best fit hypothesis. And in our previous work, we only used a very simple regression model. And here comes some result comparison, and we use the data made available by Mr. and colleagues in this evaluation. So here, the left side is we try to model only the changes happen to the verb arguments in the hypothesis space. And here is the changes happen to the world. All the changes happen to the world, and as we can see that all the changes leads to better performance. And different bars show the different ways to select hypothesis during execution, and again, the best fit hypothesis leads to better performance. But this is not the whole story. the world is full of noise and uncertainties. So instead of a deterministic representation, what we really get is more like, okay, each predicates come with some kind of a confidence value to indicate the likelihood of this predicates to be true in a given environment. So there could be different ways to handle these uncertainties. As a first step in our investigation, we augmented our framework by giving robots abilities to ask questions, okay, to resolve these ambiguities. And we identified a set of general questions, and we also used the existing data to simulate different noise and interaction, and applied reinforcement learning to learn interaction policy. So this policy will tell the robot when to ask what questions in order to get the best long-term reward. So this curve actually shows the semantic models, verb semantic models learned by using the reinforcement learning policy, and it consistently outperforms other policies. And not surprisingly, reinforcement learning also significantly improves the efficiency by asking smaller number of questions. So we implemented this learned interaction policy in our Baxter robot. And next, I'm going to show you a quick demo here. So these, what you're going to see here is the this interface here. Here is the internal robot representation of the perceived environment, and we use the ULO object recognition software here. And here are the ambiguities or uncertainties which the robots will carry the question answering to try to resolve.
Place the kettle on the stove.
I don't know how to do it. Could you show me?
Sure. This is how you do it.
After the action, the state of the kettle should be on the stove, correct?
Yes.
Sure, I'll try to reproduce this action. Put everything back and say ready.
Ready.
I'm going to perform this action. Let me know if it's correct.
Yes, that is correct.
All right.
Place the tropical juice on the cutting board.
Which is the tropical juice?
It is the pink bottle.
When you say tropical juice, do you mean that bottle?
Yes.
Sure, I will perform this action. Let me know if it's correct.
Okay, so you get the idea here. So I have shown you the two examples where modeling effect state can help grounding language to perception and action. So the action effect knowledge is important. So we humans actually acquire such understanding of action effect or cause effect at very young age. Infants around 8 months old can take simple actions to make things happen to the world. For example, by shake the rattle to hear the rattle sound. And around 3 years old, the children can make prediction about what could happen and also reason about what caused something to happen. So if robots ever going to become our partners, they need to have this basic action effect prediction ability. So to address this problem, we recently started a new task on action effect prediction, which is the third problem I will briefly talk about next. And we call this naive, is because we're only looking at very basic cause-effect relations between concrete actions and the perceived state of the world. So we formulate the problems like this. Given an action, for example, a verb-noun pair, squeeze bottle, and given a set of images that describing different states of the bottle. And the goal is for the agent to identify which of these describing the potential effect of this action. So in this case, we hope that the agent will pick these two. And similarly, given an image describing some kind of effect state and given some kind of a set of actions, the goal is to identify which action that could cause this particular effect state. Okay, here we hope the agent will pick the last one. And to address this problem, our goal is not trying to train a model using large amount of annotated data. Okay, instead, we aim to have a very small number of annotated examples. For example, given an action, what we need is the effect description and a couple positive examples and negative examples. The reason we want to have a small number of annotated examples is because we want to be able to allow the humans to teach robots new action effect through communication when new situation arises. So to supplement these annotated data, we also aim to use the web images retrieved based on the extracted effect phrases. So as we know that the web images can be very noisy, okay? So to handle that, we only applied very simple bootstrapping approaches that we put more trust on those images that are more consistent with the seed images. And we create a data set for this investigation, and the annotated information, annotated images mostly used for the evaluation purposes. And here are some of our initial results. Okay, the light is just based on the seed, and the dark bars are the bootstrapping approach. So this shows bootstrapping approach can improve the performance, but however, this is a very difficult problem. There is a large room for improvement. And I'm going to show you a couple examples here. For some verb-noun pairs, it is easier to identify or to recognize the effect states because they have unique characteristics compared to the default state. For example, the beat eggs always going to see this liquid in the yellow color. But for some others, it is actually pretty difficult to recognize the effect states because there's no distinct, unique characteristics. For example, open window or closed window, there's not much change compared to the default state of the window. So right now, we're only use the images for this investigation is because it's easier to get the image data. But what this really shows that to study this kind of action effect, we should really look at is a dynamic change and which would come from video, okay, in the future. Okay, so this action effect prediction actually plays an important role in interactive task learning. So for example, during learning new tasks, the robot will encounter new actions it doesn't have any effect knowledge. So the robot can initiate the communication with humans, okay, to either direct requests for the effect descriptions, and then from there we can generate the effect phrases, or the robot can actually go through the action effect embedding space trained from the existing data to generate this, and then this can be used to retrieve the images and then train the model as I described earlier. So we implement this in our interactive task learning system. And again, what you're going to see here is the internal representation of the perception. Here on top of YOLO, we also have the state detector of the environment. And here is the agent's existing knowledge of action effect models. So in this demo, you're going to see that existing knowledge can be used by the agent to reason about the actions and acquire action steps, which are not explicitly specified by the from human language. And also, you're going to see that the new action effect will be learned, acquired, and put into the knowledge base.
Hi, Becky. Hello, can you teach me how to make smoothie?
Yes.
What is the first step to make smoothie?
Peel the orange.
Sorry, I am not familiar with this action. Please show me what the orange looks like after peeling. How would you describe the effect of this action?
Now the orange is peeled. The skin is removed.
Got it. Here are some images I found. Please take a look at my screen. Which of these images show a peeled orange?
The first, second, and fifth.
Okay, I will learn from these images. What is next to make smoothie?
Next, you put the orange into the blender.
Okay, what is next to make smoothie?
Next, you turn on the blender.
Did you first close the blender lid?
Yes.
Okay, what is next to make smoothie?
The task is done.
Thank you for teaching me.
Hi, Becky.
Hello, please test if I know how to make smoothie.
Okay, what is the first step?
Peel an orange.
I have peeled an orange. Can you tell which orange it is?
This is the peeled orange.
Now can you tell which one it is?
This is the peeled orange.
Good. What is next?
Put the orange in the blender.
Shall we turn on the blender?
No, first you should close the blender lid.
Now shall we turn on the blender?
Yes, that is correct.
Okay, so here's a quick wrap up. And I have shared with you 3 problems where action-effect knowledge plays an important role for grounding language to perception and action. And what I have discussed mainly was the task learning related to this one single communication with humans. But this is only the tip of the iceberg. There are many directions to pursue. For example, how to leverage data, web, and collective intelligence to acquire these common sense knowledge for communication and collaboration, and how to learn a generalized structure across multiple learning experiences, and how will the communication play in such process, and how to enable learning across multiple tasks, and for example, learning by analogy from communication. And as robots acquire knowledge through their respective experience, now how to enable knowledge sharing among a cohort of robots. So these are only some example questions. The space for supporting learning from language communication is enormous. And I believe this is the exactly community that can address these questions. So here comes my last slide. In the land of science and technology, and we have seen significant advances in these disciplines. And the last 10 years have been extremely exciting for many of these disciplines. However, in the pursuit of artificial general intelligence and to realize Rosie, the robot maid, we still have a long way to go. And the journey ahead will face many challenges. And essentially, we're going to enter this underexplored territory with many unknowns. And so it really will take a multidisciplinary, dedicated effort to jointly explore this landscape ahead, to identify the junctions and jointly build pathways. And particularly for technologies to enable language communication with robots. These are the few things on my wish list. First is the representation. And as I showed in my talk, that common ground plays an important role for the successful communication, then I believe the robot internal representation will have to be rich, sufficiently rich and interpretable, so that they can bring humans and robots together to a joint understanding of the situation. And the second is about learning and inference algorithms. And I think they will have to be incremental and interactive and support lifelong learning from interactions with humans and environment. And I also think that we should provide robots strong knowledge to start with. So that would give so that would require our algorithms to be able to incorporate prior knowledge. Certainly, algorithms will have to handle uncertainties, and very importantly, need to support causal reasoning, because that's fundamental in human decision-making and action planning. And lastly, and very importantly, is this common sense knowledge. So there are various kinds of common sense knowledge, and I believe this cause-effect knowledge is very important. However, it has been less studied. So in this talk, I've shown you the action-effect knowledge related to the physical actions. But besides the physical level, we humans have a tremendous cause-effect knowledge that guide us in our social interaction and the moral judgment. And I believe these are also very important kind of knowledge if we are going to build robots that are going to live among us and contribute to our human society. With that, I'll be happy to take questions. Thank you.
Thank you, Joyce, for this fascinating talk that really does bring together the research from all three communities, ICML, AMOS, and IJCAI. There are two microphones on the sides here. If you have questions, please line up at the microphones. So, well, to get things started, and please do come up. We have about 10 minutes before the next invited talk. But I'd like to ask. So, you are bringing in aspects of learning, and you have some neural network learning in your perception, but you've also made a commitment to using logical representations, including some probabilistic aspects. Especially in this, in these communities, there's a lot of debate and thought about what are the right representations. Can we do everything with neural networks? Do you need to have, what's the role for logical representations? What's your thoughts on how to choose, and what went into your thought process about which aspects you would do with logic and which you would do with neural networks?
Okay, very good question. I think that because my goal is to really enable this communication with robots, okay? And this, as I mentioned, common ground is very important. In order to have this common ground, I believe the symbolic representation will play an important role. But to get to the symbolic representation, there are lower level representations. And I believe that once there's a significant amount of data available, like a neural network for doing object recognition, these kind of a technology can be used to build that. So I really think that these two can be, we don't have to really choose one or the other. And today we can actually just, bring the advantages of to both approaches together. I hope I addressed the question.
Yes, and I just say I fully agree with you on that. Okay. There's a question there.
Oh, thank you. Thanks, that was a really nice talk, and it's very nice that you actually close the loop of the research going back to the robots. Working with robots doesn't only allow you to have embodied students, but more importantly, embodied teachers. So the human is actually in front of the robot. And I'm wondering if there were other kind of social signals that you could leverage to help learning. Like, for example, you are mentioning Tomasello. And one of the aspects of human learning is how young children use extra information like body language or eye gaze. So I wonder if you could...
Absolutely, absolutely. The joint attention plays an important role in learning. In fact, that the basic skills allow the children to acquire the language is the shared intention, joint attention. And in our other work, we actually looked at the eye gaze and the gestures, which I have not talked about here. But certainly, I believe will play an important role. But also another thing is about human learning is, human teaching is, we actually have studies. We invite humans to our lab, but they don't really know the limitation or capabilities of the robot. They don't even know how to start. They treat robots like a real human, and then the process fall apart. Or they treat the robots like really have no mind or no intelligence. Then everything becomes so not motivated, the whole process. So it's really important, I think, that both have the human motivation in the learning and also have the robot's motivation to be cooperate, to tell the human the limitation and the capabilities of the robot. Thank you.
Thank you for the fascinating talk. I was just wondering, is this whole process biased towards the English human language, or could you also use other human languages to teach the robots?
Well, this is not typically for English. If you can see that the English is just the surface language, right? But the underlying representation is language independent. Okay, we can translate, do a semantic processing to translate that language into the representation, internal representation, then it should work for other languages as well.
Thank you.
Thank you.
So in this whole room, I can't imagine that there aren't more questions, but I'll be happy to take the opportunity to ask another one while waiting for others to come up. So in the field of natural language processing, one of the grand challenges is extended natural dialogue, being able to go back and forth. People are always pointing out how Siri and Alexa can do well for one or two turns, but get confused after that. Do you see, this is sort of a longer term question, but do you see this, the common sense that's coming out, common sense knowledge that's coming out of your work as having a role to play in being able to extend, to get closer to these extended dialogues? Right now, your dialogues are very scripted for particular purposes, but is there any direction that this helps in that regard?
Absolutely. In fact, in dialogue, right, what makes us understanding each other is this common background, okay? If we don't have the common sense, knowledge representation, common sense, and I already showed in the slides that the robot will not be able to perfectly understand what you say, right? And without such understanding, the dialogue would become a little, will break down, okay? So I truly believe this common sense knowledge will really help not just just interpreting human language, and also help the dialogue to even use the dialogue to acquire more common sense knowledge. I don't know. Thank you.
Please.
Thanks for the really fascinating talk. I guess my question is a bit more philosophical. In one of the videos that you showed, once I guess the robot identifies the orange, it takes off its arm and it almost knocks out a juicer. So my question here is that in a simple task like teaching the robot to make orange juice, there are a million little details like you have to specify. Like, okay, even if you identify the orange, make sure you don't break something or something like that. And then there's the question of robot dexterity. So while humans are very dexterous, it has taken us a long time to even achieve the level of dexterity that we have. So even to make like a robot that's really, really good at making juice, even if that's a very small task. So what gives you the hope that we will ever reach the level of Rosie, or even like what do you think of a timeline? Like when can we get a robot that can at least make juice perfectly without like mentioning every single detail?
Yes, I wish I could answer your question, but I can't, okay? And I think that this roboticist, maybe Peter can help me answer this question in terms of the manipulation, when we can have the robots that can actually, really make smoothie. In fact, right now, we're not really making asking robot to make the smoothie. So it's, as you see that we're completely based on the understanding of the action. There's no manipulation involved because we don't know how to handle that. Okay, is that okay?
Hi, thank you for the very interesting talk. I'm wondering in your action pair, if you consider using other noun-verb pairs to help with that current task. It seems really specific to what you're asking it to do. So for example, a chopped apple or a chopped onion are both chopped, and there's information about both which could be used to provide baseline level to the robot. So I'm wondering if you've considered that.
Yes, absolutely. That's what we're doing. That is, we have a nouns and similar nouns share the similar kind of affordance, and similar verbs share the same kind of causality. That's the idea. We can use these similarities in the embedding space, trying to predict, the new verb-noun pair using the existing new verb-noun pairs.
Thank you.
Thank you.
Hello. Thank you for your talk. I think you painted a very interesting picture, an inspiring picture of lines of research to make robots better companions for humans. In this conference, there's been a number of works on kind of more efficient models. The talk yesterday, one of the talks was on intelligence per kilowatt hour. I'm wondering about the extent to which you've thought about the efficiency of the models that you're employing, or to the extent that you've kind of consciously decided that's not a priority for your research.
Actually, I have to say that this field is enormous, okay? And I used to work in the virtual world, but when I start looking at the physical world, it's like an open can of worms, okay? It's like I have to address the robots, the manipulation, perception, action, so that then I kind of feel like for the language part, we have to be somehow carve out a particular space and focus on that particular research problems. But I do see that, in fact, there are a lot of things here. You see, okay, robot arms moves like really not the state of the art, okay? But I really would like to be able to collaborate with roboticists and, to solve these kind of problems. But right now, it's a conscious decision that we want to mainly focus on the representation in the language. Yeah.
Thank you.
Thank you.
Hello, thank you for the talk. I would like to ask about the following. So, for teaching the robot, we need a human. And I'm busy, I don't want to train my Rosie. And also having the human teach the robot has the other problem that I see, that a lot of work actually focuses on translating human language to a representation or a set of states that the robot understands, right? So I would like to hear your comments on approaches such as a robot learning from a robot, such as we've seen actually recently on games. Not only in the exploration of the state, for example, that they may collaborate, but even allowing them to talk in their own representation and language of their own may help. Basically, your comments on this. Thank you.
Yes, absolutely. There are many directions. So what I'm talking about is only one of these. I'm not saying this is the only. This is just one to complement with all these other approaches to teach the robot. Okay, thank you.
We have time for one last quick question.
Do you plan on sharing knowledge and abstract representations between robots, and do you think that would enable them to have a better understanding of the world in common sense and have a common understanding with their human counterparts?
So what do you mean by sharing? Like you made that visible to the human?
No, directly sharing the models that the robot is learning between different robots.
Oh, between different robots. Oh, that certainly would be an interesting direction to pursue. That's I think that that's the goal, right? If you learn from one experience, the other robot should be able to use that information. But it's not directly used, right? There could be situational differences. Then the other robot will have to address how to adapt, how to use. Okay, that's another research question. Thank you. Yeah.
All right, with that, let's thank Joyce one more time for this fascinating and ambitious talk, sharing it all with us.
Thank you. Thank you.
So please get seated. So I'm Francis Bach, this year's ICML General Chair. It is my great pleasure to welcome our second joint invited speaker. So George Tenenbaum is a professor in the Department of Brain and Cognitive Sciences at MIT. He is one of the thought leaders of our community, and he has been working at the interface between machine learning and cognitive science, with a striking ability of having great contributions in the two disciplines, as shown by the many awards he have received. Also, he has been mentoring a lot of PhD students and postdocs, and many of them are now leaders in our disciplines. So please, today he's going to talk about building machines that learn and think like people. So please give a warm welcome to George Tenenbaum.
Okay, thanks for that introduction, wonderfully generous introduction, and thank you to the organizers for this great opportunity to be here, and also to the last speaker. I think you're going to see a number of common themes in the talk I am going to give. I'm coming from a complementary perspective as a cognitive scientist, a member of Brain and Cognitive Sciences, but also an AI researcher. But you're going to see, I think, again, it's interesting. I think one way to put it is if you try to come up with talks that connect these three different communities, maybe it's inevitable what we'll come to. All right, so I'm going to be talking about building machines that learn and think like people. And in particular, I'm going to be talking about research that we've been doing at MIT and with a number of other colleagues and other institutions in the Center for Brains, Minds, and Machines, and also as part of this new institute-wide initiative at MIT that we call the Quest for Intelligence. I'm going to be talking about the work of a number of current students and postdocs, as well as some alums and faculty colleagues. I tried to list most of the key people here. If I forgot your name, I'm sorry. I'm going to try to, it's a lot of work here, and I'm going to try to single out, as we go along, the really key project leaders. And I just have to say I've been incredibly lucky to work with all of these people on what, to me, are really the most exciting questions we could be thinking about. It's an amazing time to be asking these kinds of questions in between the cognitive sciences and engineering, because we have all around us AI technologies, right? But in a very real sense, we don't have any real AI. What I mean by that is that we have machines that do things that we used to think only humans could do, and they do them very well. Sometimes they beat the world's best. But none of these machines has anything like the flexible, general-purpose common sense that each of you use to learn to do each and every one of these things, if you choose to, and an infinite number of other tasks that you could learn. So what's missing? What's the gap? That's what I'm trying to figure out. Okay. Now, there's many things that are missing, and it's a long way away before we have anything like that level of general-purpose AI. But the particular gap that I've been focusing on is summed up in this slide. What is the really distinguishing feature of recent AI technologies, of course, as everybody here knows, is the recent successes in pattern recognition. That includes, of course, deep learning, but other data-driven machine learning methods that have really just nailed this problem. But intelligence is so much more than pattern recognition. In particular, it's about modeling the world. So that means not just finding patterns in data, but actually explaining and understanding what we see. It means being able to imagine things that we haven't seen yet, maybe that nobody's ever seen, and then to make plans and solve problems to make those things real, and then to be able to build new models as we experience more about the world, so learning as model building. If you're interested in these themes, I'd refer you to this article that came out in Behavioral and Brain Sciences last year with a number of excellent commentaries and some responses that I wrote together with several former students and postdocs and colleagues, Brendan Lake, Tomer Ullman, Sam Gershman. We explore these issues at great length, probably too much length, but if you want more than this talk, start there. Okay. I think we have to admit, right, that we are very far from being able to capture human model building at anything like the kind of level of engineering maturity and scale that Silicon Valley would like. And yet, what I want to tell you about here is I think there is at least one route to try to get there, which is to reverse engineer how these abilities work in the human mind and brain. And this is the fundamental principle of our Center for Brains, Minds, and Machines, and the part of the quest for intelligence at MIT that I've been working on. That the basic science of how intelligence arises in the human mind and brain can lead to fundamental advances in the engineering of intelligence if we approach our science like engineers. So here's our quest grand challenge. Imagine if we could build a machine that actually grows into intelligence the way a person does, that starts like a baby and learns like a child. I've been working on this project with a number of colleagues at MIT and beyond. Here I'm just showing you 3 of them, Laura Schultz, Rebecca Sachs, and Elizabeth Spelke. And together, this is what we're trying to tackle. We think that success would mean artificial intelligence that is in some sense truly intelligent, and machine learning that actually learns. Okay? And it's a long way away, but that's okay because we know that even small steps towards this goal can be huge. So consider the history of deep learning and reinforcement learning. Just here's a few snapshots. Some of the original papers where the basic mathematics of these world-changing algorithms were first published. I just want to draw your attention to when and where they were published. They were published decades ago, in the 1960s, 70s, and 80s for the most part, in journals of psychology or computational neuroscience or general science journals like Nature. These were papers written by, some of them were by mathematicians, physicists, psychologists, engineers. In each case, these are small steps, just trying to give some basic mathematics of some of the simplest learning processes in animals. Think Pavlov's dogs. But what we've seen is that these small steps, when engineered at scale, can change the world. So think what we could do with the next small steps, especially if these were small steps about actually trying to understand how human children learn. Now, this is probably the oldest idea in AI. It was, among other things, introduced here in Alan Turing's famous paper, where he also introduced the Turing test. This paper, published in 1950, well preceded all of these other papers I showed you there. And it's been championed by many others for good reason, right? Human children are the only actual known scaling route to human-level AI in the known universe. They're the only system we know that reliably, reproducibly, demonstrably grows into a human intelligence, starting from something less than that. So if we could engineer that or understand how that works in engineering terms, well, what other route would we need? Now, of course, we all have to ask, if it's such a good idea, why hasn't it worked yet? And I think, to be honest there, we have to say that it's really only now that all the relevant fields are, I think, mature enough to talk to each other. In particular, I think it's only now that the science of how children actually learn, the science of cognitive development, as represented by some of those colleagues of mine that I showed you there, and many others, is at the point of maturity that can offer real engineering guidance to AI. And hopefully AI is at a point of maturity where it can take that guidance. And it's really needed, I think. The basic questions that we have to address, right, what are the engineering questions if we want to do this, is what is the starting state? How do babies actually start? And what are the actual learning mechanisms of children? And you could be incredibly brilliant, like Turing, but unless you study the science, all you can do is presume how these work. And Turing, as brilliant as he was, presumed wrong, and he was quite honest about it. He didn't know, right? So to just highlight a line from his famous paper, presumably, the child brain starts out something like a notebook as one buys it from the stationers, rather little mechanism and lots of blank sheets. But what we now know is that's just completely wrong, basically. So again, echoing very much of the previous speaker. So for example, in the classic work of Elizabeth Spelke, she showed, by studying babies as young as 2 months, 3 months and older, that children don't just initially see the world, the youngest babies, as just patterns and pixels, even high-level ConvNet features, but rather in terms of objects. That means physical objects in the three-dimensional world, objects that don't wink in and out of existence or teleport or pass through walls. Okay? In a very real sense, they are already born prepared with object permanence and knowing about three-dimensional space. Rebecca Sachs has studied similar things as well as the basic social cognitive mechanisms, the way babies understand other people. And she's shown in recent work, this was from a recent paper based on functional magnetic resonance imaging of 4 to 6 month old infants, that the high-level functionally specific brain circuits that we see in adults for, say, understanding other people and other parts of high-level perception in large forms are basically already there as early as you can look in babies' brains. And Laura Schultz, who studies the learning of older children in what's often known as the child as scientist view. So, for example, very much developed and popularized by Alison Gopnik or Susan Carey and others who study children's learning. They study all the ways in which children's learning is nothing like just copying things down from the blackboard, but an active process of forming theories about the world and doing experiments, the experiments that we call play, in order to test those hypotheses actively. So, in other words, what we've learned is that the starting state is rather more sophisticated than we might have thought. And the learning procedures are also rather more sophisticated than we might have thought. We have supervised learning and reinforcement learning, but we also have these much more powerful mechanisms in humans. And that raises the challenge for engineering or reverse engineering. How are we going to capture those in machine terms? So that's what I'm working on. And I'm focusing on intuitive physics and intuitive psychology. I'll illustrate what I mean in a second, but again, very resonant with, I think, what you saw in the previous talk, because while I'm not really going to be talking about natural language here, these abilities are also, among other things, the building blocks for our first words and our first phrases, and then the window that all that gives us into the rest of the world of human meaning. A key stage here, again resonant with the previous talk, is the stage of 18-month-olds. So consider this 18-month-old here on the left who's stacking up cups, a popular kid activity, all right? And think about the intuitive physics that lets him do that lets him assemble these cups into a tower, that lets him make a plan where he's, after failing to fit that one cup on, he's going to make a sub-stack of 2 cups and put it on the 3. Okay? And then to debug that plan at multiple levels when it might go wrong. Now, for those of you who work on robots, or everybody else here because you're sophisticated consumers of robotics, all right, we know this is far beyond what today's robots could do. And if we could build robots that had that level of the ability to think about, let alone manipulate the physical world in their plans, then that would be amazing. Or when we talk about intuitive psychology, here I'm going to show this famous video again of Felix Wernicke and Michael Tomasello, another 18-month-old. And what you'll see here, the subject of an experiment, now this is a famous experiment where there's that kid in the back, the 1.5-year-old, okay? And he's seeing, just like you, an action that he's never seen before. And you haven't seen this before either unless you've watched this video, okay? But just like you, he can understand what's going on and how to interact, right? Just watch here. It's amazing, right? So think about the common sense that has to be going on inside that kid's head to be able to do that, all right? Again, there's intuitive physics to understand the action, what are the constraints, but then there's the goals and the plans, there's the joint attention, the eye contact, the quick look down at the end to the person's hands to make an inference about how the plan's going to be complete. If we could build robots that could do that, that would be incredible. Okay, so again, far away, but that's where we're trying to get to. Now, in the work that I'm going to be talking about here, I'm going to tell you about some of the first steps we're doing and the basic kind of technical tools. This isn't going to be a very technical talk, but again, I'll try to include pointers to the more technical work. But just to highlight some of the tools, one is the idea of probabilistic programs. Okay, these are a new generation of AI programming languages, and like I'd say most of the rest of AI, having the right programming language is by no means sufficient to make progress, but it is often necessary or extremely valuable. So think about how much TensorFlow or Torch or PyTorch have contributed to deep learning. So the term probabilistic programming means different things to different people, but this is what it means to me. It has about as much to do with probability as neural networks have to do with neurons. Namely, it comes out of trying to think about some basic issues in probabilistic modeling and how to build general tools that capture what is essential to probabilistic models. But at this point, it's expanded to include programming languages which really allow us to combine a number of the best ideas in AI from multiple generations of trends in the field. So not just, of course, the most recent developments in neural networks, but also the ideas of probabilistic inference in graphical models, especially causally structured models, and even before that, the idea of symbolic languages. These tools, the tools for abstract reasoning and composition that you have in symbolic languages, and the tools for reasoning under uncertainty, for grasping causal structure, and then in hierarchical probabilistic models for being able to learn flexible inductive biases and learn to learn, combined with advances in neural networks and deep learning for pattern recognition, are incredibly powerful when they come together. And I think if there's any technical message to take from this talk, it's that we shouldn't have to, and really we must not feel forced to choose between the power and advantages of these ideas, but rather develop frameworks that allow us to combine their strengths. And at this point, there's a number of exciting probabilistic programming languages. For example, recently the Pyro language being developed by Noah Goodman and colleagues at Uber AI, or languages like ProbTorch, Bayesflow. You might recognize names. Gen is a language being developed by Vikash Mansinga and colleagues at MIT. And all of these languages have the same goal to integrate these excellent ideas. Now, it's not enough just to have a general purpose programming language. You have to say what kind of programs are you going to write. And for us, the way we're trying to capture the basic common sense knowledge of young infants is with probabilistic programs that are built on a core of game engine programs. So the tools that game engine designers use to create a rich or the game engines provide to game designers to allow them to create many rich, immersive experiences, many new games, without having to program everything from scratch, but that give you fast, real-time interactive graphics or fast, real-time interactive physics, none of which, is perfect. In fact, it doesn't have to be right. It just has to look good on short time scales and be efficient enough to interact with in real time with the user. Those, we think, are the same kinds of engineering considerations that shaped the human brain and other animals' brains over evolution. And we think that to a first approximation, the tools of game engines can describe in some way, okay, not too literally, but in some way, what evolution has given us as far as these common sense modeling abilities. Okay? That also extends to what you might call simple kinds of game AI, or tools for allowing non-player characters to interact with the player by having some kinds of perception and planning abilities. So, I think many people at this point in AI and robotics and machine learning use game engines to generate training data for machine learning methods, right? But our suggestion here is that there's a game engine in your head, that these tools are not just a way to make a simulated world, but to capture the way your minds simulate the actual world. By wrapping these game engine programs inside probabilistic inference frameworks, that's how we're going to try to reverse engineer these capacities here. Okay? Another way to put it is if you want to understand the arrows on this diagram, you could interpret this, for example, this intuitive physics sketch over here as something like a hidden Markov model. But there's no way you could capture it with the standard tools of hidden Markov models, fixed finite dimensional state vectors, or transition matrices, or observation matrices. Rather, we use the tools of game graphics and physics engines to make these thick arrows have the right kinds of abstract properties to capture the real causal structure of how graphics and vision and physics works. So for the rest of the talk, I want to show you how we're using these tools to try to answer these two questions. First, how do these systems work? And then how are they learned? Okay. For a talk at ICML, there's only going to be some learning here, but I think it's important to understand what is learned before we can talk about how to learn it or how to learn with it. So let's talk about intuitive physics, for example. So in work going back a few years that really started in our group with Pete Battaglia and Jess Hamrick, who are now both at DeepMind, we published a paper about 5 years ago in PNAS for us, the informal title was the Intuitive Physics Engine. It had a somewhat different name, something like Simulation as an Engine of Physical Scene Understanding. But what we tried to do there was to show how we could take simple kinds of game physics engines, wrap them in a framework for probabilistic inference to answer many, many different kinds of questions of intuitive physics. Like, for example, when you see these stack of blocks, some of them look like they should be falling, others of them look stable, some you can't tell, and we might ask people to judge on a scale of 1 to 7 how likely any one of these towers is to fall. That's what you see. The average judgment of a group of participants is on the y-axis. And then we ask our game engine the same thing. Now, there's some uncertainty in both humans and in our model. Our model's uncertainty comes from the fact that we can't perfectly estimate the 3D state from an image. And then we might also be uncertain about exactly which forces are in play. There's gravity, there's friction, there's collisions, but there could be, the table could be bumped or there could be a wind. And the combination of those things allows this model to make very good quantitative predictions of people's judgments. So the model's predictions, the average of a few posterior samples in the game engine are shown on the x-axis. And in the paper, we used the very same model to answer questions not just about will the stack of blocks fall, but which way might they fall, or how far will they fall, or here's a little bit of language, I would say. Suppose I tell you that the gray stuff is 10 times heavier than the green stuff. So I can just tell you that in words. And there's a language interface to your game engine program. So you can set the mass or the density of one material. And then that's going to change how you make predictions. So here you see, for example, two geometrically identical towers. But because they're colored differently, and if you know that the gray stuff is 10 times heavier, you'll think one will fall one way and the other will fall the other way. And both people and the model make similar predictions. Or you might make inferences backwards. So if these scenes, which might look to you surprisingly stable, if I say, well, maybe the red stuff or the yellow stuff is a lot heavier than the other, can you tell from looking at these which one is it? So the same models can do that too. Let me just show you one of the more unusual kinds of inferences that we studied in this paper, because it shows you how having these kinds of probabilistic simulation tools allow you to answer questions not just like, will the stack fall, which again, we've all had lots of experience with and maybe could use a pattern recognition approach for, but a question that, unless you've seen me give this talk before or read the paper, you've probably never thought about. So here's a task. I'm going to give you this task not through a data set, but through English. Okay? And the question is this: what if this table is bumped hard enough to knock some of the blocks onto the floor? Is it more likely to be red or yellow blocks? So let's make this interactive. So you guys tell me, red or yellow? Okay, red. You got to be loud so I can hear you in this big room. Okay. How about here? Here. One more. Okay, all right, you all got to experience the joys of experimental psychology. And what you saw happen here, if you could hear what everyone was saying, was the same kind of things we observe in the lab. So sometimes you're sure what the answer is, and everybody responded quickly and loudly with the same answer. Other times there's uncertainty across people, or sometimes that uncertainty also shows up in response latency. You're a little bit longer to answer when you're not sure. So what's going on inside your head to be able to answer that? Well, we capture this with the same kind of model that I just showed you, and we can get basically about the same quantitative accuracy on this task as we did on the much more familiar task of how likely is this stack of Jenga blocks to fall. And the way we capture it is by doing something like this. Here's a little window into one of these simulations. Let's see if I can click this thing here. So here I'm just showing you a small bump of the table in our game engine. And here's a big bump. Now notice, of course, that at the micro level of all the individual blocks, different things happened each time. But at the level that matters for intuitive physics, for the judgments I'm asking you, exactly the same thing happened. Namely, all the yellow blocks went over and few or none of the red blocks. And also note that to answer this question, you don't have to run the simulation for very many time steps. So even just a few time steps, so I wanted to stop it there, even just a few time steps like that, or here, even just a few time steps, that's enough to answer the question, to make a reasonable guess. And it doesn't have to be a very high fidelity simulation, and there's no way that you're going to run a high fidelity simulation for this highly nonlinear system over more than a few time steps. But just a few low fidelity samples are enough, maybe even just one, to make a reasonable guess. So that's the basis of this system. And it's built without any learning at all. I'm not saying that there isn't learning involved in building it in a human child. We'll come to that in a little bit. But the point is that the same system can be queried to answer an endless array of questions, just like your mind. And that's using the tools of this probabilistic simulation program. Okay. Now, what about on the intuitive psychology side? So here, we're building on tools that are very familiar to everybody in this room. In fact, many of you helped to develop them originally. It's the basic idea that, again, is grounded in early developmental psychology of what's sometimes called the principle of efficiency, or has been developed, or principle of least effort, or has been developed recently by several developmental psychologists that I work with, Julian Hara-Edinger, Laura Schultz, and others, and Hyo Guan, in what we call the naive utility calculus. But the basic idea that from very early, with some evidence even again as young as 3 months, babies understand that when people act in the world, especially when they reach for things or move around in space, they're trying to act efficiently. They're trying to, in some sense, maximize an expected utility function that takes into account the rewards of getting their goal and the costs of their actions. And that basic cost-benefit calculus can be, that's effectively the metric for a planning function, and then that provides the basis for inverting the plan to observe actions and work backwards to infer an agent's beliefs and desires. And in a number of studies going back 10 years or so in our lab, we've basically taken the idea of, taken state-of-the-art robotics tools or AI tools for probabilistic planning, embedding them in a Bayesian framework, which the tools of probabilistic programming let us do and make formal. And then that becomes models of action understanding as we work backwards to make Bayesian inferences about the beliefs and desires that explain actions. I'll just show you two examples of that, two of the nicer recent examples. So one is from some work that Chris Baker and Julian did together with me and Rebecca Sachs. This is what we call the food truck scenario. But it's just one scenario in what we studied in a paper that was called Bayesian Theory of Mind, where we're basically taking a POMDP, partially observable Markov decision process, as the model of planning, and then saying, okay, well, if we assume that we're seeing an agent solving one of those POMDPs, can we work backwards to infer their reward function as well as their initial belief distribution? But both the reward function and the beliefs are highly structured around a common sense representation of physics. So to be concrete, imagine this scene here. This is a snapshot of, let's say, your local university campus, where if it's like my university, many people often go to get their lunch from food trucks that come and park in different places on campus on different days, and you go to your favorite truck or somewhere else if that one's not there or closed or the line's too long and so on. Okay. So in this particular part of campus, there are 3 trucks that come on different days: the Korean truck, the Lebanese truck, and the Mexican truck. And there's 2 parking spaces, which are shown in yellow. And so you can see that on this particular day, the Korean truck is down there in the bottom left, and the Lebanese truck is there in the upper right. Okay, but on different days, it could be different trucks, Mexican truck, or the spots could be empty and so on. There's also a building in the way, and our friend comes out of this building where they work, and they only have line of sight perceptual access. So we know that. So they can only see, for example, the near spot. Now, what do? Well, they walk past it, around to their side, where now they can see the Lebanese truck there, and then they turned around and go back to the Korean truck. So the question, which we ask people, I'll ask you, is which is our friend's favorite food truck? Korean, Lebanese, or Mexican? You guys tell me. Very good, Mexican. Okay, so that is, how interesting is that, right? I think it's very simple, but it's very interesting because the Mexican truck isn't in here at all. It's not like, I mean, if you see me, reaching for a cup of water, of course you might think, well, I just want a cup of water. But here, what you see is our person following an efficient path, not to something in the world, but to something which we understand they are mentally representing. They have a false belief, or at least a false hope, that they thought that the Mexican truck might be there, but then it turned out that it wasn't, right? So that's the kind of judgment we get. We have people make graded judgments about their preference for the different trucks, and for Mexican is the most preferred one, and Korean second. And then they also infer that most likely the agent thought that the Mexican truck was going to be there, otherwise it wouldn't have been worthwhile. It would not have been efficient to go there. If you were sure the Mexican truck wasn't there, since Lebanese is your least favorite, the efficient thing would have been to just go straight to the Korean truck. Okay. And that pattern of inference we can study in this experiment across really dozens of these different scenarios. I'm just showing you 4 here. And the same model explains all of them. Again, it doesn't require any training. There's just a couple of parameters basically calibrating the costs and rewards. And it provides a very quantitative fit, even more accurate than the intuitive physics models. I'll show you just one more thing that's just in progress, where we're applying the same kind of idea more in a, call it a grounded robotics AI setting, where we're watching a person now with video. We have both video and Connect reach for one of a number of different objects. In this case, I'll show you a video in slow motion where she's reaching for one of 16 objects in a 4x4 grid, and you have to decide which one she's reaching for. Okay, so I'll just say, raise your hand. It's going to play in slow motion. Raise your hand when you think you know which of those 4x4 objects she's reaching for. Okay, there's all the hands went up. All right, so yeah, you saw there was an initial wave of confidence. Some people weren't sure, and then everybody's hand went up. Okay, so roughly like that dashed black line there. Now that's not data from our experiment. That's the predictions of our model. How does that work? Well, we have a causal generative model, which is based on the Mujoko physics engine, which again, many of you know and use. But this is a physics engine designed for multi-jointed, even whole-body humanoid motion planning and object manipulation. Okay, and it's very natural with that tool to express in the forward causal direction, the most efficient path towards any of these targets. So then we can turn this, we can embed this in a Bayesian framework for inference by just considering all the different hypotheses and seeing which one best fits the data. So the bars there show you the Bayesian posterior, which is exactly what you saw as the basis for those dashed lines. Now, if all we were doing was reaching for objects on the tabletop in front of us, of course, there might be simpler ways to do that using just low-level motion cues. But consider all these other kinds of activities. Like, for example, if somebody starts from a sitting position, you might see that you can figure out a lot about what they're reaching for before they even start to move their hand or their arm, just by how they move their body or torso. Or consider this guy over on the right there. That's Tao, one of the collaborators here. You'll see him doing a rather weird thing. Maybe you can see what he's reaching over. If you can't tell what he's reaching over, you know he's reaching over something. But still, you can figure out that there's some weird constraint, but you can figure out what his goal is even before he gets to it. Okay? And the same model can explain those things because they're all about physically efficient action with your whole body subject to the constraints of the visible constraint of the table, or maybe the invisible, that's a glass plate. Okay, no computer vision system, if we're just trying to do a bottom-up vision system, is going to detect that glass plate because it's literally invisible. But yet you still know it's there as part of understanding his action. Or consider scenes like these, which are now multi-agent systems, right? What makes the scene in the upper left look like somebody's helping somebody else, right? You have to figure out the first person's goal and the help. Or the scene in the lower right look like not helping, but maybe the opposite. Okay. So the way we try to capture that, and I don't have time to show you the details, but we've captured this actually with some developmental psychologists. We've instantiated these models in ways that we've tested with adults and also with babies. And the basic idea is to use a kind of recursive utility calculus. Again, this is very standard in game theory and some of the multi-agent things, actually some of the work that Peter Stone has done, for example, where you have utility functions that depend on both agents, or where, for example, one agent represents their utility to be a function of another agent's utility, right? If I take your expected utility as a positive component in mind, that's almost the definition of what it means to be helpful. If I take it to be a negative component, it's sort of a negative. It's a hindering, right? Think about the way we talk about the golden rule or analogous kinds of principles of what it is to be a good actor in a multi-agent setting. This is a way to implement it directly. And we think that, we have even some preliminary evidence, that even young babies are doing calculations like that when they watch agents move around in the world. I'll just show you two examples of baby experiments. So this is a baby intuitive physics experiment that we did with Erno Teglis and Luca Bonatti. Actually, they did the experiment. They did almost all of the hard work. But Ed Vool and I built a model which basically took the same kind of probabilistic physics engine model and showed how it could capture infants' graded expectations about which object would appear when in a range of different scenarios here. And I won't tell you the details other than just to say the basic kind of method is the same one that's used by Spelke and many others in the infant literature. To get a sense of what do infants know, well, you show them things that should be more or less surprising, right? You try to violate their expectations. And if you violate their expectations, they look longer. And what this study showed was that you could turn that into a graded signal, that infants were more likely to looked longer the more surprised they were, where surprise we could predict based on basically the inverse of probability in a probabilistic physics engine. And we vary a number of different factors of space and time and number and shape attribute to make a range of predictions there. Or on the intuitive psychology side, I'm going to turn up the sound a little bit here and hope you'll be able to hear it because it kind of helps. We're looking at how infants use the same kind of cost-benefit calculus to infer how much an agent values a goal. This is work that was recently done by Sherry Liu and Liz Spelke, but also with Tomer Ullman in joint Harvard-MIT project. So let's see. You may not be able to hear it. It shouldn't matter too much, but what you see here is an agent who is faced with a costly choice and declines it, and then faced with another equally costly choice and accepts it, in a sense, to get to a goal. So we might say, okay, well, clearly the red guy likes the yellow guy more because he chose to go to the yellow guy and not to the blue guy. But this is a much more controlled experiment. I'm just showing you two of the videos. Across the experiment, infants see the agent makes the same number of moves towards the yellow and to the blue, but some are higher cost than others. Okay? And by varying cost, and here cost is really physical work done, it's important that this builds on the kind of intuitive physics. These are 10-month-olds that we already know 10-month-olds are sensitive to. So the cost, the physical work done might be how high do you jump over a wall, or a ramp that you have to roll up that could be steeper or less steep, or it could be a gap of different sizes that you have to jump across. And in each of these cases, infants take the cost that an agent is willing to pay to get to a goal as a sign of how much they value that goal. Okay. Now, it's notable, and I'll come back to this in a little bit, but it's notable that in these and many other infant experiments, notice how different they are from real-world imagery. They're cartoons, basically, right? And I think that's important if you want to think about, say, learning these things based on some kind of system that's trained on the end-to-end from scratch on the infant's real-world visual experience. I think it's pretty clear from looking at how infants deal with these abstract stimuli that there's something very abstract and conceptual in the way they understand intuitive physics and others' actions, intuitive psychology, costs and benefits, even from the beginning. So that's going to turn us now to the second part of the talk, which is, where does learning actually come into the picture? If we can see some versions of these abilities in young children, how do they get there? Okay. So one answer, what I just alluded to, is that somehow these systems emerge, mostly from scratch, in each baby by learning in some end-to-end way from raw pixels what is needed to support prediction and interaction with the world. Okay. Now, this isn't a crazy idea. I don't think it's the right one, but some of the smartest people in our field have suggested it and worked on it. So one of the earliest versions of this was some work that Ilya Sutskever and Jeff Hinton did a little bit before the deep learning became officially the thing. But in their work on recurrent temporal restricted Boltzmann machines, they tried to basically learn the physics of bouncing balls from scratch. Or in some very nice recent work from Facebook AI, led by Adam Lehrer and Rob Fergus and others, they took very much these same kind of block tower tasks that we've studied, and trained, basically a deep convnet with a little bit of extra stuff, but not too much more, to predict will the blocks fall over, and something about the pixel flow to get more supervisory signals. On some very interesting recent work from DeepMind. And there's a number of papers in DeepMind that embody this philosophy, and in some sense, much of DeepMind's philosophy of AGI is really summed up by this view. But in some very nice recent work that's explicitly inspired by the same kind of science that I've been talking about, Matt Botvinnik's group has looked at infant intuitive physics and generated some training and testing data sets that are sort of cartoon versions of the same thing, as well as some similar kinds of theory of mind displays. And again, I think all of these things are very interesting. The machine theory of mind, which was presented at this conference, I think is especially interesting and synergistically connects with some of the work that I was just talking about in ways that I'm happy to talk about afterwards or in questions. Okay, but still, I think that the basic idea which you see in all of these approaches, which is you're trying to learn in an end-to-end way, something like the intuitive physics or intuitive psychology representations I'm talking about, based on just trying to predict what's going to happen over some time scales in space. I don't think that's consistent with the data that we have from infants, and I think there's a long way to show that this is actually going to work, even if it's not the way infants do it. It's a long way to show that this is actually going to build something as generally useful as these systems already are in infants. And here I come back to the cartoon versus real thing, right? So in these sorts of displays, they are tested on cartoon kinds of displays, or they're trained on and tested on the same kinds of displays. Cartoon grid worlds are very simple cartoon physics displays. And they show, again, impressively that they can generalize to other instances that were not exactly like those, or even somewhat different than those in the training set. But the generalization is not huge, and it's not to anything like the full range of images, real or synthetic, that even young babies can see these things going on in, even before they've had really almost any training experience. So I think that's just fundamentally different what these systems are trying to do and what infants are trying to do. Okay. So the approach to learning that we've been pursuing is there's a few different directions, and I'll just try to summarize them quickly. But they're basically, some of these are learning with or in this game engine in the head, and others, which I think are the biggest and hardest problems, so hard that nobody has a good solution at this point, is how do you actually learn something like the game engine itself? So let's talk about, for example, learning to use the game engine in the head, because I think this is the clearest place where in the research program that we're developing, the tools of neural networks and deep learning are clearly valuable and clearly a good way to go. And what we're talking about here is pattern recognition, but the patterns are patterns of conditional inference. So this often goes by the name of amortized inference or inference compilation, for example. Noah Goodman, Frank Wood, a number of others have developed this kind of idea, at least in the probabilistic programming community, but well beyond people who say they're doing probabilistic programming, there's versions of this idea. Okay, this is an ideal thing to do when you want to make inferences that go against the direction of causality, when you want to invert causal arrows, basically. So you want to, say, invert graphics engines, in other words, do what we call vision. And you have lots of experience, okay, and you have lots of opportunity to train a system, essentially, to do this, okay? And it's really important to get it right, so you might even dedicate some brain circuitry to it. So that's the kind of thing we've been doing, for example, in Vision, and I'll just show you a little bit here about some work that, again, I started doing together with Vikash Mansinga, Tejas Kulkarni, who's been developing some very interesting kind of analogous ideas, actually, that he also presented at ICML. And Pushmi Kohli, and I'm just sort of highlighting two students who've been leading the main efforts that I'm talking about here today, Jiajun Wu and Junyan Zhu. Okay, so the basic idea is to take the graphics pipeline, for example, how scenes are structured with objects and how that gives rise to images via important intermediate representations, like, for example, a z-buffer, something like the depth to the nearest visible surface, or analogous kinds of representations of surface normals that help you do some real-time shading. And to turn those around and to say, well, maybe we can train an inverse graphics engine, in other words, a vision network, okay? And the key idea here is to exploit the generative model in a couple of ways. Sometimes I say this is like Judea Pearl meets Jeff Hinton meets David Marr. Hopefully some of you know what I'm talking about with all three of those folks. But the generative model, both in sort of like Hinton's wake-sleep algorithm, the generative model provides the training data for the recognition model. So you might not need any actual real-world labeled images. But also the conditional independent structure of the generative model, if you exploit that in the recognition model, it allows you to learn recognition networks or vision networks which can be learned much more efficiently, which are much more robust and much more generalizable. Okay. So here's a way we've been doing this in something that we call MARNet, again in honor of Marr, for the specific problem of 3D object reconstruction. So a number of people in computer vision are working on this, and our approach is good in some ways, but it has a lot in common with other approaches out there, which I don't have time in this talk to tell you about, but feel free to ask about that. But the basic problem that we and others are trying to do here is to take a 2D image of an object, something like an ImageNet type image, where there's basically one object in the center of view, and then we want to reconstruct a dense, accurate 3D model, something like a voxel grid reconstruction of the full 3D shape, or it could be, we could use point clouds or meshes, and the community is actively exploring different kinds of representations. The key thing here, we happen to be using voxel representations, but the key thing in this work is the intermediate representation, the idea of these 2.5D representations, like what Marr called a 2.5D sketch, or what's also sometimes known as intrinsic images. Again, it's something like an image-based map of depth or surface normals or silhouettes, or we might also talk about albedo or the object's reflectance, okay, which is a natural representation in the graphics direction. The conditional independence is it's the variable that renders the 2D image and the 3D shape conditionally independent, right? To a first approximation, at least, something like the depth and surface normals map contains all the information about 3D shape that's in the image and screens off all the other stuff that makes the image interesting to look at and realistic, but not actually causally relevant to the inverse shape problem. Okay. So we implement that idea in a neural network, which is explicitly trained to go through these several stages. Okay. It has training losses for the intrinsic images, like the surface normal map. Okay. And then it has a sort of a 2D and a 3D convolutional structure, and it's trained to produce a 3D voxel reconstruction. Okay. By setting things up in this way, you can actually train this network completely from synthetic or imagined data from the generative model. You have to start off with a bunch of 3D shape models, like for example, chairs or other objects, and then you imagine them in different positions against different backgrounds, okay? But that provides training data for multiple layers of this network. And again, we also can use the graphics online in perception for what's known as reprojection consistency. Again, a number of groups have used this idea, and we're developing that here too, which helps basically fine-tune small differences, or fine-tune the 3D shape interpretation to really fit the actual surface normals. And because we know the causal structure of how 3D goes to 2D via 2.5D, and we know we only have to go back to 2.5D, then that's a powerful assumption and makes this work efficiently. And you know, this method can provide surprisingly good 3D reconstructions for objects in a familiar class like chairs. Okay. Now, we can extend this idea also to full scenes, and Jajin together with Pushmeet Kohli built something which they call the neural scene renderer. This was a CVPR paper from last year. And they use this to render into various graphics engines. You can think of it as like a generalized autoencoder, but where the decoder is actually a game graphics engine. Okay? And now we can apply that same idea to the graphics physics engine combination of, let's say, our blocks world scenes. Okay? So here the key is that the input to the graphics engine is the same as the input and output of the physics engine. It's this three-dimensional, object model. Okay? And that's really important. Okay. So the system here learns to see the blocks, learns to see where they are, their size, shape, and color, and then that provides very fast ability to actually see the scene, and then we can make inferences about what's going to happen next, and even imagine what's going to happen next by using our actual symbolic physics engine. So it's a kind of neuro-symbolic hybrid. Here I'm showing you on some of the scenes from the Facebook AI group. They took real movies. You'll see the real frames on the left. And you're going to see in a second those movies, what happens when these blocks, when we turn them on and the blocks fall. And then I'm going to show you on the right a resynthesized movie showing what our system predicts is likely to happen. Okay, but our system just sees the first frame, then it de-renders into the state of the game physics engine, and then it makes a guess by running forward the game physics engine. So here we go. I'll show that to you again. You can see that our prediction is not exactly right. But it's right enough. Again, at the level of intuitive physics, it's about right? Maybe the thing falls a little bit too soon, maybe it doesn't fall in exactly the right direction, but basically the right blocks fall in basically the right direction. I don't think people can predict any better, and that's the kind of thing we're testing experimentally. And you may not need to predict any better for most purposes that matter. And again, this is a challenge and an interesting constraint for robotics. Here's a few more movies just so you can see that. Here's one more. Just think for yourself, like, okay, what do I think is going to happen? Okay, now I'll show you what our system thinks is going to happen. All right. So again, I think this is a nice combination of pattern recognition where it's tractable on the vision side with a model-based approach for the physics. And having that physics model in there with real forces, we can actually use it for planning. So if I want to say on that scene there, pick up only the green block or keep the blocks from falling, then the system tells me where I can apply forces in 3D, although I'm showing you here in 2D. So the lesson on this idea of learning to see, in a sense, is that thinking about the conditional independent structure of probabilistic generative programs gives us really useful guidance on how to integrate neural nets into the toolkit, It tells us when and where to use neural nets when we're inverting causality. It tells us what training targets to use, namely the simulator state, for our dynamics model. It gives us key intermediate representations, the bottleneck representations in the simulator on the graphic side, such as the 2.5D sketch. And it also tells us how to come up with training data, which we can generate just from within our head. Now, we can also talk about learning actual resources in the game engine, like learning the objects. So again, in some really nice work that Jiajin Wu did together with Chengkai Zhang and others at NIPS 2 years ago, they built a 3D GAN. This is one of many such things at this point, But just basically trying to say, okay, well, let's say I want to build a generative model of objects at the voxel level. We can do that, okay? If we know about objects. You have to know about objects and you have to know about 3D, okay? We can use that as a prior. This is a paper that was just accepted to be presented at the next ECCV, which shows that by incorporating that basically into MARNet, you can get even better 3D reconstructions for a wide range of, or a somewhat wide range of different image categories, chairs, airplanes, cars, and so on. Still far from perfect, but it helps. Okay. Some really cool recent work that Junyan did together with Jiajin and a number of others is to kind of extend this approach to include a full shape texture generative model which can actually produce realistic looking images. So here you take a 3D GAN, the same kind of one we had before, and now you have the generative pipeline, 3D, 2.5D, 2D, and you build also a texture model. It's also a adversarially trained generative texture model. But the key is you're using your knowledge of 2D and 2.5D and 3D. So the texture is something which is basically mapped onto the 2.5D sketches in order to produce, for example, a realistic shape as well as a realistic image of a car. And compared to other GAN results, which again are really quite exciting and impressive, and I'm certainly impressed with them along with many others. But here we can take a step to make much more realistic kinds of generative models for objects because we're modeling both the 3D and the 2D structure jointly. And the representation is disentangled. It explicitly separates out the shape, the pose, the texture or texture and color, and those can be independently manipulated. So again, it's another nice hybrid of using neural networks for what they're good at in pattern recognition, but thinking about the symbolic, compositional, causal structure of objects in a three-dimensional world. Okay. It's also not nearly enough. So in work that I've been working on pretty much for my whole career, it's not really the focus of this talk because I think a lot of people know it. Certainly the work that Brendan Lake did on the Omniglot data set with Russ Salukudinov and I, it was in Science. It got quite a lot of attention. Many people here have used this data set, and there's quite, I think the machine learning community knows what we're up to here, so I don't need to tell you guys about it. But this is part of a long-term research program that, for me, goes back to my PhD thesis in trying to understand how human children can learn new concepts, including new words, but new concepts for object classes from just one example. So like our CAM example, if you've never seen a CAM piece of rock climbing equipment, one example is enough to pick out the others. And here we tried to tackle a simple small step to that in Brendan's work with these handwritten characters in many different languages, each of which, right, you can see is its own thing. It's its own simple visual class that you can learn from one example. You don't need thousands of examples like an MNIST, okay? And the Bayesian program learning model that we introduced tried to use the tools of probabilistic programs to tackle that problem. So basically what the BPL model for the Omniglot dataset consists of is a multi-stage probabilistic action or drawing program, right, which captures the strokes and substrokes and their relations that people use to actually draw characters, okay? And then, by inverting that in a Bayesian fashion, we can infer from a single example of the action program, sufficient to again, generate convincing new examples that even pass a kind of Turing test. So if you haven't seen this before, you might think this is a little bit cool. I always think this is cool because I always forget which one are the humans and machines. So here's the Turing test. Given one example, we can ask our algorithm and also 9 people to make up an instance or a new instance of this character, not to copy it, but to just draw another one. And here I'm contrasting the humans and the machines. It's different in each case, but see if you can figure out which ones are the machines. It's not easy. Think about it for a second. Maybe somebody will get it right. Okay, I'll show you the answer now. So those are the machine. Raise your hand if you got them all right. In this big room, somebody should get them all right, but probably about 1 in 2 to the 6th of you got it all right. Most people get about 3 out of 6 because most people are at chance, all right? Now, this is just one simple small example, one baby step, right? But in recent work and ongoing work, we and a number of others are trying to take the same approach to many other domains of one-shot learning, for example, in speech or gesture or other kinds of more realistic objects. Some steps that we're excited about, Kevin Ellis, who's a PhD student in our group, together with Daniel Ritchie, a professor at Brown, have used similar kinds of ideas, also enabled by a kind of neural network visual front end, to try to learn graphics drawing programs for hand-drawn diagrams, also from one example, and to capture the abstractions in them and to generalize. There's an archive paper on that, but it's also submitted. Or recently, Yanglong Tian and Jianzhen Wu and others have taken a similar approach to learning very simple kinds of shape programs for 3D things. But this, brings me to the very last topic, because I think of all of these here as really just warm-ups for the most interesting hard problem, which is how do you actually learn the full common sense simulator of the world? How do we learn the game engine itself? In other words, could we build a program learning program? Could we build a program which takes the kind of experiences that you might have as a young baby or over evolutionary time? Because if much of this knowledge is built in through evolution, then in some sense these program learning programs might have to be more like evolutionary programs. But can we somehow build a program that constructs from experience a physics engine, for example? And if we want to think of it developmentally, could we say, think about what's going on in the mind of a baby who over the first year of their life reliably goes through certain stages. Here I'm pointing to the work of René Bayer-Jean, but also Spelke, who I've mentioned a few times, and many others in infant research have mapped out with very clever experiments, and admittedly, not a whole lot of data, because it's very hard to come by infant data, so there are big error bars on these numbers. If you're taking a picture of the slide, that's great, but just note, take everything with a big grain of error bar salt. But we do know something about how infants' intuitive physics develops, let's say, over the first year. And so we might ask, can we capture these different stages of knowledge with different kinds of probabilistic physics programs, and then can we capture the transitions between them with some kind of program learning program? Okay. Now, this is a very hard problem. We joke about it as the hard problem of learning because it's much harder than, say, deep learning. Still deep, but hard. Because if you're talking about search in the space of programs, there isn't anything like a nice, smooth optimization landscape, right, where you can just use stochastic gradient descent. Rather, it's there's no nice, simple topology or geometry, and rarely any way to compute gradients in the space of all possible programs. Okay. So how do we solve this problem? Well, there's a couple of approaches, right? One approach is to try to turn it into more of a differentiable programming problem, turn it into the kind of thing that you could use, for example, gradient descent, by trying to represent your physics engine in neural network terms. So that was effectively what was going on in this slide I showed you before, right? And as I alluded to, it sort of works, but it doesn't really work. It doesn't, you can train on images of 3 balls bouncing around in a box, and you kind of get a model that sort of captures 3 balls bouncing in a box. It doesn't generalize to 4 balls or 5 balls or 10 balls or boxes that are shaped differently, let alone all the rest of intuitive physics. Now, there's been some really exciting recent developments along this direction. A little bit from our group. So Michael Chang, who was an undergrad at MIT, he's now a PhD student at Berkeley, he built something called the neural physics engine. But a lot of other work, especially coming out of Pete Battaglia's group at DeepMind, on various kinds of graph-based networks, such as interaction networks and relation networks. But what all these things have in common is an interesting neurosymbolic hybrid. They're all trying to learn physics engines, but they put into the system, it's pre-programmed knowledge, that the world has objects, okay, and the objects, they have object permanence, the objects have properties like mass, they have location, and there are events, like when 2 objects might interact with each other. So there are relations and at least sometimes even events, okay? But then they learn, using distributed representations and neural networks, they learn something about the laws of how forces work. So sort of trying to learn, you could say it's kind of like learning F equals ma and something like the particular forces in play. It could be gravity or forces of collision. And what these systems are able to do is to generalize in much more significant ways. So they can generalize to many different numbers of objects and to different kinds of object configurations, all right? And I think that's a nice case study that shows the power of putting in the right kinds of symbolic knowledge about objects and events that seem to be in infants' minds from the very beginning, and then trying to learn the rest. I think it's still an open question, one that I'm somewhat skeptical of, but totally open to, and people in many groups are working on this. But it's an open question whether this can scale up to learn abstract physics that generalize in much more substantial ways as even infants do. And I think another approach is kind of coming from the opposite direction, is just to bite the bullet and say, we're just going to learn that game engine by programming. So you can say, well, why don't we learn a game engine the way programmers write a game engine or write a game? You might be saying, mostly I could start with the game engine, I just have to learn the game of my life, right? Now that's really hard. But the idea that learning might be like programming, I think this is one of the most important, exciting frontier areas. And this is the sort of direction I want to leave you with. It's the one direction that I'm personally most excited about in learning. I think it's very hard, but I think it sort of has to be right. So think about, when you write programs or when you code, think about all the ways you try to fulfill the goal of coding. What is the goal of coding? It's making your code more awesome. It could be more accurate, but it could also be faster or more elegant or more reusable or explainable or any number of things. Okay? But think about all the activities that advance that goal. Sometimes making it more accurate or faster is tuning parameters. Okay? Sometimes the compiler does that for you automatically. Sometimes you do it by hand. Sometimes you use gradient descent. Okay? But think about all the other ways that you make your code more awesome. You extend or refine existing functions. You write whole new functions. You borrow functions from other people. You borrow a whole library of functions. You write your own library of functions. You maybe write a whole new language. Okay? All of those activities of coding have analogs in children's learning. And I think that if we really want an adequate reverse engineering account, a computational account of how children learn, we're going to need to capture all of these in machine forms. And that means algorithms that write algorithms. Now, you're all lucky if you're interested in this, because you could go to the NumPy workshop on Sunday, which stands for Neural Abstract Machines and Program Induction, which is a gathering of one of the places, this is the second one of those, the first one was at NIPS 2 years ago, where people who are bringing together machine learning and programming languages techniques, as well as other ideas from cognitive science and AI, are really working on this hard problem. I'll just preview one of the papers that Kevin Ellis, who I already mentioned, is going to present there. This is joint work with Armando Solar-Lezama, who will also give a talk there, on what we call Dream Coder, which is it's a kind of a wake-sleep algorithm for learning to write code. It's a system which, kind of inspired by the way humans consolidate their knowledge in sleep, learns to write new functions and indeed whole new libraries of functions. It bootstraps domain-specific libraries with a wake phase where it tries to solve problems, and two kinds of sleep phases. One in which you consolidate out abstractions. Basically, you make your language more rich that then allows you to express new functions in a more compact way. But there's also a neural network that helps guide the search, and that can also be trained in a sleep phase, much like the Helmholtz machine, the original wake-sleep algorithm. So just to wrap up then, I've tried to give you a window into a research program that is somewhere far along, but really just in its early stages, asking how can we capture the basics of human common sense, our understanding of the world in terms of physical objects, intentional agents, and their interactions that we see from the youngest infants. How can we capture that in engineering terms? What's the content of this knowledge? How is it used? And how is it built? And I've shown you how some of these new tools, from probabilistic programs, game engines, along with just these hints about program synthesis and program induction, are starting to be able to tackle these problems. But very clearly, we're just at the beginning of this challenge. And it's just a super exciting time that we're able to maybe tackle AI's greatest dream, the idea of being able to build a machine that starts like a baby and learns like a child. And I'll leave you with what might be a roadmap, how we can address the most basic questions, which is what is the inductive bias, how do we start, and how do we learn? How do we capture the ways in which it's not just a blank slate, and it's not just reinforcement learning or gradient descent, using these tools that I've talked about. And I want to just leave you with a couple of thought points that challenge some of our conventional machine learning or AI wisdom. When we look at human learning mechanisms, we see these mechanisms which are really mechanisms that help us revise and construct inductive bias. They don't just work within an existing inductive bias when we're learning with programs. So this is a way we can benefit from strong starting conditions, just like all other species, and yet be able to revise these inductive biases, make them flexible. In other words, inborn or present from birth doesn't mean inflexible. Okay? So we should think about that and not just assume that hard coding something or hand coding something means that it can't be recoded. Also, think about if much of learning is something that happens through evolution, then that's a very different process from gradient descent, and AI researchers might want to gain something from that, thinking that way. And finally, if we think about real learning in the sense of the learning that happens in a child's mind, it might be much more like thinking or programming than like gradient descent. But that's okay, because if you like gradient descent, because gradient descent is highly synergistic, right? Learning programs could actually be tractable in ways similar to end-to-end learning of differentiable programs or neural networks, and neural networks might even help to make that tractable. Okay, thank you.
Thank you, Josh, for these very inspiring talks. So we have time for a few questions. So if you want to ask a question, go to the mic and raise your hand. Okay, Tom?
Hi, Josh. Wonderful talk. Thank you very much.
Thank you.
Are there things in the infant data that you cannot explain with the combination of probabilistic programming and a game engine?
That's a great question, and I think it's hard to say because we and others have barely tried, right? I think there's going to be some things. I mean, if by probabilistic programming you also include neural networks, I think that's important because you have to handle whatever are the learned visual procedures, right? But it's quite possible that there will be, in fact, quite likely that there are things that have to do with cognitive resource limitations, like just visual working memory, which is similar but more limited in infants. And another thing that you see when you look into the infant literature is that infants, in many ways, are like adults, but slower. You can see this in neurophysiology, actually, and you can see this in behavior. And apparently, it might even be true for infant monkeys. So it might be that some of the things that infants seem to not do have to do with just slower processing speeds that have more of a hardware explanation. and not so much of a learning explanation.
Thanks.
Somebody over here.
Oh, hi. Thank you so much. It was a very interesting talk. I was just wondering, like, you could imagine that as a deep learning person, I could accept your premise of innateness that, you know, gradient descent isn't going on within a lifetime.
Yeah.
But we have methods like deep meta learning where we could imagine that gradient descent is going on between lifetimes. And so basically the idea is like, okay, if I accept innateness, I don't necessarily have to change anything about my methodological, you know, day-to-day AI practitioner stuff. Why should I not only accept innateness, but then also hop over to this more structured approach?
Yeah, no, that's a reasonable question, and I'm glad that some people are pursuing that, and I'm also open to pursuing that. But the main thing to think about there, right, is think about the difference between what we know, at least, to be the algorithms of evolution versus the algorithms of gradient descent, right? I mean, there's some similarities. You could talk about a fitness landscape, but even there, it's very complicated because in real evolution, things are changing, you know, it's a multi-agent and multi-species world. But also, I think the main thing is that evolution in the sense of like, you know, constructing genetic programs that then unfold in development to build brains, right, and bodies. That is doing something like program induction. It is doing discrete search through a big space of programs, developmental programs. We don't know that much about how those programs work, but that is our best way to understand it. And you know, in some sense, it has many of the characteristics that you might not want in a learning algorithm. It's slow. It has to be massively parallel on a level that even DeepMind or OpenAI are still not ready to grapple with. And you're going to have lots of false starts. You can't guarantee how it's going to come out. It might not be repeatable, right? So it might be that we're going to have to consider, even if you want to, you know, build learning algorithms that meta-learn what evolution learned, that they're going to have something more like the character of evolutionary search or evolutionary computation. So whether it's genetic algorithms or genetic programming, I think, and again, I'm far from alone in thinking this, that the techniques of genetic programming, which were also popular around the same time that neural networks were popular, their last wave, the late 80s and early 90s, they're also poised for revival. And the only reason that we haven't seen a revival of those techniques on the scale that we've seen neural networks is that they were going to require orders of magnitude more computing power to pay off, and we're still waiting for that. We're still waiting for the GPUs, and we're still waiting for the AlexNet equivalent of that. So I would put my money and time on that direction in addition to the direction you were talking about.
Thank you.
Hi, thank you for the talk. The question is, how can you reconcile the fact that you describe the progress of learning like in a Piaget sequence, where you build skills, more elaborate skills, on the top of simpler skills. And what we can see in other, say, realms is the fact that the progress is made by pruning. You have something which is a big space, and then you manage to find something, and then the next progress is by removing details and removing everything you can, right, and simplifying this.
That's a great question. I'm not sure why you think I characterized learning in Piagetian terms. I never said that, and I actually said the opposite, in the sense that Piaget thought of object permanence as a learned skill, whereas I cited Spelke for talking about how it might be innate. But I mean, I think it is true that when AI researchers talk about development, they're usually, if they're talking about science at all, they're talking about Piaget, which is great. Piaget was very inspiring, but that's kind of like talking about Turing, right? I mean, Piaget is that old. And he was the brilliant founder of the field, much like Turing. He lived a lot longer and got to write a lot more and do a lot more. But, you know, I'm looking to much more recent research in infant cognitive development and children's learning that paints a different picture, including one that I think is consistent with what you're talking about. I think that is certain. That's one way. There are many ways to write code. If you think about these activities, right? Some of them look like pruning. Some of them look constructivist. Some of them look like, you know, writing sort of abstract code and then filling in the details. So I certainly don't think that children's learning always proceeds from concrete to abstract. In fact, often the evidence is that it goes in the opposite direction, right? Maybe because the abstractions are wired in, as some people have suggested in language, or maybe because actually what we've called in some of our work the blessing of abstraction, that actually sometimes the abstract stuff is the easiest and first thing to figure out, and then you fill in the details. Again, much like a human coder who figures out maybe the high-level abstract structure of their program before they actually write the specifics, and often good code is written that way, starting from the abstractions and the high-level structure, and then filling in the details.
The last question from the right.
Thank you. So this idea of using game engine for data augmentation to be used to generate label training data for learning system is great. And it works while we are in the gaming engine and also physics. But however, when we bring the psychology in, it means that there are subjective differences, person-specific differences that cannot be modeled by noise or just considered as a upper bound of the noise. Is actually inherent differences based on the theory of mind, even you mentioned.
Yes.
So how do you incorporate
No,
that?
that's a great question. Let me just first clarify that what I'm talking about is very similar to what a lot of people do, which is using a game engine for data augmentation. But I'm suggesting something a little bit different than that. I'm suggesting that might be where all the data comes from. But you're right to point to the difference between the graphics and physics part is much easier. In part because that's just been the way it's always, graphics and physics are evolutionarily ancient because they're physically ancient in the world. But it's important here that, the phase that I'm talking about, especially when I talk about learning with the game engine, is really from 0 months up to about 18 months, okay? And it's important that the intuitive psychology of 18-month-olds is limited, right? It's not the full theory of mind. Okay, there's some evidence that 18-month-olds can represent false beliefs, but only when those false beliefs are about where an object is in space. So I only gestured at this here, but I'm happy to talk more about it, and we've written some things on this. I think that the tools that you do have already in game engines, in which agents have very limited abilities, very limited notions of beliefs and desires, which are really just about the space around them, the things, the objects, their locations, their relations, and beliefs which are formed based on perceptual access, like what I can see, and goals that are about getting one object in some relation to another. That to a first approximation captures a lot of at least the youngest infants, I think, intuitive psychology. Now we form much richer forms of intuitive psychology, but especially once we have language, right? So if I were to maybe just leave you with one final thought about where this goes beyond the 18-month-old stage. And here I'm not being original, but channeling Liz Spelke and a number of others, I would say you could very roughly divide human learning into 3 stages. Again, it's also resonant with the last talk from Joyce, that there's sort of the 0 to 18-month stage, which is everything up to the very earliest stages of language, when children are just starting to learn words and just beginning to put a couple of words together. That's basically all you learn before language is really online in a full adult way. Then there's the next couple of years from, say, 18 months to age 3 or so, 3 to 4, where the main cognitive achievement is to learn language, right? Is to use that first stage to ground out your early semantics and syntax and pragmatics. And then once you get to 3, basically, now you've got enough of a fully functioning language system that you can ask questions and learn from the answers that people give you. So you start to learn things in language. You have to ask, why did you do this? Why didn't we do this? And your theory of mind transforms and everything else transforms. And that's just the 3rd phase of learning, which is age 3 up to the whole rest of your life, where it's really through language that we learn most of the rest of what we learn, including a much richer intuitive psychology, as well as many other aspects of culture, morality, and so on.
Thank you.
Thanks.
Let's thank Josh again.